All right, so we're going to talk about some of the many widespread applications of multiple integrals, double and triple integrals specifically. And so the first thing that I want to remind you of is that we've already talked about a very important application. And we're going to kind of split this up into two dimensions, double integrals and triple integrals. So recall that the volume of a region R is given just by sort of symbolically writing the triple integral over this region of just a bunch of volume elements. So we basically just break the region up into a bunch of small volume elements and we add them up, and that's the volume. Easy enough. Of course, the difficult part is actually setting up the triple integral as an iterated integral, etc. But we have the same idea for the area of a region. But this time we're just going to do a double integral over the region because there's only two dimensions or variables to integrate over. And again, we just break the region up into a bunch of area elements, small area elements that we call dA, and we just add them all up. And as long as we set up the integral correctly, we're going to find the area. So now suppose that this volume region or this area region is actually a physical object. Then it has a volume, but it also has a mass. And so what is mass? Remember that mass is going to be, well, in the case of the volume, I'm going to say this number delta times volume. Okay, and so what is delta? Delta, well, it's just the mass per unit volume. And we can say the same thing for the area. We can say that the mass of an area region is just, well, I'm going to use a slightly different letter. Instead of delta, I'm going to use the Greek letter sigma times the area. And I guess I really don't have to make this distinction, but sigma, we're going to say, is the mass per unit area, because we're dealing with an area instead of a volume. Okay, so that's how we find the mass of a region. But there's a problem. This is assuming that the mass is uniformly distributed through the region. Or in other words, the mass per unit volume is constant. It's not changing. And then the same thing for the area. We're assuming here just this simple multiplication equation to find the mass, that the mass per unit area is constant, or in other words, the mass is equally distributed over the area. And now that's not always the case. In general, we have something like this. Maybe delta is a function of x, y, and z. So it actually depends on where you are. So you can think about a ball that's more dense in the center of the ball and less dense on the outside of the ball. We're not just going to be able to find the volume and multiply it by a number, because that density is actually going to be changing. And the same thing for an area region. We can think about the mass per unit area is actually being a function of where you are in the area. So maybe you have some kind of disk area region that's more dense around the outside, or something like that. So how do we actually find the mass of a region if the densities, whether that's volume density or area density, are changing? Well, all we do is, instead of just integrating the function 1 over the volume elements, what we want to do is we want to integrate over what we're going to call mass elements, dm. And we're going to do the same thing over here. And now notice I'm writing this as a single integral. And I mean, you really shouldn't think too much about it. I mean, the only reason I'm writing a triple integral here is because when I actually am going to evaluate this, I'm going to do a triple iterated integral. And here it's going to be a double iterated integral. But here, this is just kind of like a physics idea. I'm just saying I have a bunch of mass elements and I'm adding them up. Now I might be adding them up as a triple integral or as a double integral, but these mass elements are the single things that I'm adding up. So I'm just writing this as an integral. But now think about what a mass element is for a volume region with a given mass per unit volume density. Well, the mass element is just going to be the density wherever the mass element is, so delta of x, y, z, times a volume element. So it really is just density times volume. But you see that here I'm sort of localizing to one point that actually really will have constant density. And I can do the same thing over here. So a mass element is just going to be, well, wherever I am, I just take that particular mass per unit area and then multiply by that area element of where I'm at. Okay, so here's the mass that I want. So mass, we'll just say m is equal to this. And now when I set it up as a iterated integral for a volume region, well, I just integrate over the region this density function, delta of x, y, z, over the volume elements. And now here I can sort of pick a coordinate system. I can do spherical, cylindrical, regular Cartesian, whatever I want, but I'm integrating over the region this density function. And I'm going to do the same thing here for the area region. The mass is just going to be the double integral of the mass per unit area over the area elements, like that. So that's how you find the mass of a region, whether it's a volume region or an area region. So recall that after we talked about area and volume of regions, we also talked about a related idea, and that was the average value of a function over a region. So I'm going to kind of stop making the distinction between area regions and volume regions and just specifically talk about volume regions and just kind of make the caveat that everything I'm saying about a volume region is going to apply to an area region as well. So if I have a function x, y, z defined on a region R, then the average value, which we denoted f hat or f bar, is just, well, the integral over that region divided by the volume of this region R. And of course I can make the same definition for a function defined as a function of two variables over an area region. But again, we'll just think about, for now, in terms of three variables and volume regions. Okay, so an important example, or I should say related example, it's not exactly the average value of a function, is the center of mass of a region. So recall that we just discussed how to find the mass of a volume region or an area region. So we can also talk about the center of mass. And even though I said it's not exactly the average value of a function, that's the way you should think about it. The center of mass is somehow, well, intuitively, it's just where, if I took the mass and I wanted to find kind of where all the mass is centered around, kind of if I take the average of where all the mass is, there's one point, and that's the center of mass. That's the point that, if you want to apply a force to it and have it accelerate the fastest, you want to apply the force at the center of mass, otherwise it might rotate or something like that. it's a little bit easier for area regions to kind of give a heuristic for the center of mass. And so if I have some sort of area plate, the center of mass is where I can actually set it on the end of a pin and it will balance. So it really is just kind of an averaging of where all the mass is in a volume or an area. Okay, so how do we find where it is? Well, it's very much related to the average value of, say, a function over a region. So the center of mass is a point in space, or in the plane if you're dealing with an area, of x bar, y bar, and z bar. And what are x bar, y bar, and z bar? Well, x bar is more or less the average value. So this is the center of mass of some region R. So I'm going to integrate over this region. So I'm actually going to write this as a single integral because you're going to see why. So I integrate over this region the function x, but I integrate over mass elements. Okay, so it's a little bit different than average value. So average value is adding up function values over volume elements. Center of mass, I'm really weighting the mass elements by what their x coordinate is. And so that's sort of giving me the average of all the x coordinates of all the mass. And the same thing for y and z. Okay, so the last thing I need to do, well, I integrate this function x, but I also need to divide by the mass of R. Okay, and then the same thing for y bar. I just integrate over the y coordinates, the mass elements, divided by the mass, and then the z coordinate of the center of mass, I do the same thing. I add up all of the z coordinates over the mass elements, and then divide by the mass. And again, if I have my volume region, something like this, just kind of give a little sketch like that. Then the center of mass is going to be a single point in my region R, where somehow, if I go out in any direction, I have an equal amount of mass. So it's all balanced out around this point in the center of mass. And yeah, I'm sure that you've had experience with this. Your center of mass is kind of your balance point. Sort of if you yourself wanted to lay on a bar and balance, you would want to put, approximately where your center of mass is, on the bar, and that would allow you to more easily balance. So it really is just an averaging or a balancing. And just as a note, so recall that when we're adding up these mass elements, we're really thinking about the density of the object. So if the density, if there's more mass over here, then that's going to sort of pull the center of mass closer to where there's more mass, if the mass is not evenly distributed. But in the case that a region is uniform, so if R is uniform, and now what I mean by uniform is that the mass is uniformly distributed, or in other words, that the density is constant, it's not changing as I go about the region, and then we give a special name to the center of mass. Is called the centroid. So that's kind of a cool word, centroid. So when you see the word centroid, it just means, well, center of mass, in the case that over my region, whether that's a volume region or an area region, the density is constant. Okay, so there's one more topic we want to talk about, and it's a little bit more complicated. than the last two examples we've given, just finding the mass or the center of mass of an object. And what we really want to consider is what's going on when an object is rotating. Okay, so here's kind of the setup. So we have a region R. Say it's something like this. So just some sort of volume region, call it R. And then what I have is what's called a axis of rotation going through the center of the object. So this is called the axis of rotation. Not notation, rotation. Rotation. And so what's going to happen is the object is going to rotate about this axis. So it's going to rotate like this in space. So you can think about the axis rotation of the Earth. The mass is a region that has a mass, and it's spinning about an axis. And then what we want to do is say, well, how well is an object able to spin? So certainly, some objects are easier to spin than others. Now, in sort of a linear motion sense, all we really care about is the mass. So if I have a semi-truck that has a lot of mass, it takes a lot of force to move it. But if I take a feather, it does not have a lot of mass. It does not take a lot of force to move that. So we want to sort of think about the analog. So if we take an object that has a mass, that mass is going to be sort of distributed somehow about the axis of rotation. How that mass is distributed is going to make it harder to spin or easier to spin. And the idea that is going to give us sort of this analog of the mass for rotation is called the moment of inertia. And somehow, this is just rotational resistance to spinning. Mass is kind of resistance to moving. Moments of inertia are just resistance to spinning. So the higher the moment of inertia of an object is, the harder it is to spin, the more torque you're going to have to apply to spin it. Okay, so what is the moment of inertia? Well, if I take my volume region here, and I look at sort of a shell of a constant radius about the axis of rotation, like that. There we go. Then about the axis of rotation, this mass is going to spin. Okay, so what we're going to do is we're going to define basically, however much mass is here, it has a distance that we'll call r. So r is the distance a mass element, say dm, so if we just think about like this little piece of mass here, if we call that dm, so r is going to be the distance a mass element dm is from the axis of rotation. So somehow the further the mass element is from the axis of rotation, the harder it is going to be to spin. And then of course the greater the mass element is, the harder it is going to be to spin. So we're going to capture that by saying that a kind of an element of the moment of inertia we'll call di is going to be r squared dm. So we take a small little mass element located at distance r from the axis of rotation, and then kind of that element of the moment of inertia is r squared dm. So again, you see that this moment of inertia element is going to be greater if you're further away from the axis of rotation and if you have a greater mass. And that should make sense. Of course, if you have more mass, it's going to be harder to spin. If you're further away from the axis of rotation, then think about like a long rod. Even if it's not that heavy, it's still hard to spin because so much of the mass is far away from where you're trying to spin it. So then, of course, the total moment of inertia of the region I, well, we just add up the moment of inertia elements di, or in other words, we sum over the mass elements their distance squared from the axis of rotation. And that's the moment of inertia. And now I'll say that, sort of hinted by my drawing here, we kind of want to treat mass elements that are cylindrical around the axis of rotation, because if you think about a cylinder, like a cylindrical shell, all of the mass on the edge of that cylindrical shell is going to be the same distance. So it's going to be nice to think about cylindrical coordinates when thinking about moment of inertia. Alright, so here we want to show that the volume of a right circular cone with radius r and height h is this familiar, or maybe not so familiar, formula 1/3 pi r squared h. And then the volume of a sphere is, again, you may or may not know this, 4/3 pi r cubed. And the nice thing about this problem is that it shows you that there's some, kind of obscure formulas from geometry, but they don't come from nowhere. They sort of come from a uniform way to think about finding the volumes of regions. So let's start with the cone. So I'm going to sketch the cone in the following way. And you'll see why I'm doing this in a second, because we actually already have a relatively good way to describe a cone in 3 dimensions. So here's x, y, and z. And so I can think about this right circular cone region as being bounded between a cone with a vertex at the origin, like we've seen before, being cut by a plane given by z equals h. Okay, so I said z equals h, that's going to be the height of the cone from the xy plane. And then the radius will be capital R. Okay, so I'm going to use cylindrical coordinates to compute the volume of this cone. Because if you see, this z coordinate is going for a fixed x and y, really in a circle, going from this bottom surface all the way up to this plane z equals h. So our first thing to do is just to figure out what this bottom surface is, what this bottom cone is. Now we know that for some cones, or a specific cone I should say, the equation is z squared equals x squared plus y squared, which in polar coordinates is just r squared. So in other words, z is just r if we're looking above the xy plane. But that's assuming that r is just kind of increasing in one-to-one correspondence with z. But now the slope of this line, if I look kind of in the zy plane, may not be 1. In this case it's 1. But here it's actually, I'm going up h over r. So actually my cone is not z equals r, it's going to be z is equal to h over r, the slope, times r. So that's how much z increases. That's how the radius of these circles, that's kind of making up the slices of the cone, are going to increase. Okay, but that means that z is going from this surface up to the plane z equals h. So I can set up my inner cylindrical integral as h over big R times little r up to h, and then I just have dz. And now z is going from h over r times little r to h for x and y fixed in a circle of radius r. So you see that if I kind of project down onto the xy plane here, my x and y coordinates that I'm fixing are living in a circle of radius r. So r, little r, is going from 0 to big R, and then, per usual, theta is going from 0 to 2 pi. And then we have r dr and d theta. So this is giving me the volume of the cone in cylindrical coordinates. Now there are other ways to do this, but this is the way I think about it. So it's just a very simple, polar coordinate. I'm basically just integrating over a circle, and I'm going from the cone, the surface that is the cone, and I'm cutting it at the height that I want. So let's actually evaluate this integral. Okay, so the inner integral, the z integral, is pretty easy to evaluate. It's just going to be z evaluated at these two endpoints. So in other words, h minus h over r times little r. And then I have r dr d theta. Okay, notice I can factor out an h, since h is just a constant. And then I really just have r minus r squared over big R. And then we have dr d theta. Okay, and then we just keep finding antiderivatives. Find an antiderivative here. This is going to be, well, this is pretty easy. So I'm going to get little r squared over 2, and then I'm going to get r cubed over 3 over big R, but I'm just evaluating at big R, so I should just get r squared over 2 minus r squared over 3. Now notice I get capital R cubed over 3 divided by r, which is just capital R squared over 3. Okay, this is looking good. And then this is just a constant, so if I integrate theta from 0 to 2 pi, I get h times 2 pi. And then what is this constant? Well, this is just a half minus a third, which is 1/6. So r squared over 6. But let's simplify that a little bit. So this is just 1/3, because I have a 2 over 6, pi capital R squared h, which is exactly what I wanted to get. So great. So if you ever forget the volume of a cone, just pull out your triple integral techniques, set up the iterated integral, and you'll see it's 1/3 pi r squared h. Okay, so now let's take care of the sphere. And now, not surprising, because we're finding the volume of a sphere, we're going to use spherical coordinates. And so let's actually just draw our sphere. And really, I want to look at the cross-section of the sphere. That's normally sufficient in these diagrams, but we'll just sort of attempt to draw this out. That is not very good. So there's kind of my cross-section down. Well, this is going great. There's that, and then I'm going back this way. Okay, there's my sphere. Good enough. And so recall that, I didn't really talk about this as much with the cone example, but for a sphere, all I'm really doing to find the volume of a sphere is I'm just adding up volume elements like that. And so, the cool thing here is, so for a little volume element in my sphere, dV, as long as I just describe it, well, I'm just going to describe it in spherical coordinates, I just have to think, all right, well, where am I going between? Well, for rho, I'm just going from 0 up to the radius of the sphere. For theta, I'm going all the way around, because a sphere includes all of the angles, 0 to 2 pi. And then the phi angle, which is from the positive z-axis, goes all the way down to the minus z-axis, so 0 to pi. And so really, maybe not surprisingly, this is kind of the marquee, spherical coordinate example almost, where, again, theta is going from 0 to 2 pi, and then phi is going from 0 to pi. That's actually the full range of phi, if you recall from spherical coordinates. So this is the full range, kind of all possible angular directions, 0 to 2 pi for theta, 0 to pi for phi. I was just waving my hands around like you could see me, but yeah, so you can just see, if I'm looking here, I'm looking at sort of all possible angle combinations around me. The sphere is covering everything. And then rho is going from 0 to r. And then now I just need to express dV in spherical coordinates, which recall is rho squared sine phi, and then I have d rho, d phi, d theta. All right, so this is just more or less an exercise in spherical coordinates. So here we have 0 to 2 pi, 0 to pi. This rho squared, when I take an antiderivative, is just going to be rho cubed over 3, but I'm going to evaluate at capital R. So I get r cubed over 3. There's where the 3 is coming from in the 4/3, by the way. And then we have sine phi, d phi, d theta. All right, and then, okay, so I'm really just integrating sine phi here. So an antiderivative, well, let's factor out r cubed over 3, first of all. 0 to 2 pi. And then I just have cosine phi. And let's see, that's actually going to be minus cosine phi, evaluated from 0 to pi. But what is this? Okay, so cosine of pi is -1, minus cosine of 0 is 1, so -2, but it's negative, so I just get a factor of 2. So this is 2 r cubed over 3, and then I'm just evaluating over theta from 0 to 2 pi. But I'm just going to pick up a factor of 2 pi. And so you see the final answer is 4/3. So that 2 makes that a 4. And then I have this factor of pi and r cubed. So there's the volume of a sphere. In case you ever forget, there it is. All right, so we're going to find the mass of this region, this ice cream cone-like region. So let me just first draw what's going on. So, we've already seen in the previous example this cone, and I'm actually here just going to draw the cross sections. I'm basically going to ignore the theta direction because theta is really just going to rotate this symmetrically about the z-axis. So let's say this is y here, and this is z. I won't even bother drawing the x-axis. What am I doing? Y is over here. So I won't even bother drawing the x-axis coming this way. And so we have the cone, And now remember, this is really z is equal to r. Because x squared plus y squared is really r squared, and then z squared is r squared, but z is just r if I just want to kind of take this top ice cream cone part. So there's my cone. It should be straight. And now notice z is equal to r. Okay, so r is actually just extending linearly as a function of z. Okay, and then we have the top of the sphere, which is going to be like this, which, you know, I'm looking at this cross section. So in the cross section, it really is going to be a circle. And the circle is going to be, so this is the plane x equals 0, so it's going to be y squared plus z squared equals 1, just in this cross section. But of course, I mean, really, it's x squared plus y squared plus z squared equals 1 if I sort of allow this to rotate around the z-axis and actually, you know, fill out what I want it to be. Okay, so here's the region. Now if I wanted to find the volume, I can just do it. I would probably want to use spherical coordinates, which I'm going to use spherical coordinates anyway. So a couple things I want to notice is that this angle, because this is like the line y equals z, because z is you know, z goes a unit, r just goes a unit. So this angle really is just pi over 4 with the positive z-axis. Okay, that's just coming from this cone, just being z squared equals x squared plus y squared. But what's interesting is that the density is not constant. And this is really what we were getting at kind of during the lecture. And so somehow, I'm going to probably do a poor job of explaining this, but somehow, as we get further out, the mass is getting more and more tied together like that. So it's starting less dense and getting more dense towards the end. And what I want to do is look at actually a mass element. So might be hard to see right there, but I'm just going to take a little mass element and describe this mass element. And so I'm just taking a shell like this because the density is going to be constant. And so the density, it says, is proportional to the distance from the origin, but the distance from the origin is just rho. So the density is really just k times rho. So this shell of mass element I'm taking has constant distance from the origin. So in other words, the density over the shell will be constant. So in this case, it will just be delta times, well, the volume element, and we'll talk about what the volume element is. Okay, so delta is really kp, and k is just a constant here. Not kp, k rho, here we go. So k is the proportionality constant. And then what is dv? Well, the thickness here, the thickness of my volume element is d rho. Okay, and then somehow, you know, where is the angle going between? Well, the angle is going, you know, the sort of the width this way, you know, I'm going from 0 to pi over 4. And so I have something like rho times pi over 4. And then I'm going all the way around for theta. Like I said, we're going from 0 to 2 pi. But we actually have to kind of project that down. So, I mean, I'm just sort of describing what this mass element is. And so I'll probably just leave exactly like I have it. I think I'm kind of oversaying what I need to say. So we have a mass element here that's just the density, and the density is going to be constant over this mass element. And then just times the dV, and then this density is just the proportionality constant times rho. And what we want to do is we want to add up over this region R all of these mass elements. That's the point. So we just have described the mass element as being the density times the volume element. And so let's do it. So this will be the triple integral of delta, which is just Kp, K rho. And then we'll just describe this in terms of polar coordinates. So theta is going from 0 to 2 pi, as we said. And phi is going from 0 to pi over 4. Okay. And then rho is going from 0 all the way up to the radius of the sphere, which is 1. So 0 to 1. And then we have k rho, which is the density. And then we have dV. But dV is rho squared sine phi d rho d phi d theta. Okay, so all that to say, we're just putting in this density function that's just k times rho. All right, and so we have rho cubed that we're integrating. Notice that theta, we're just going to get a factor of 2 pi. If I integrate, there's nothing in here that depends on theta, so this is just a rectangle in the theta coordinate. So then we have 0 to pi over 4. And then we can also factor out this proportionality constant. And then we have 0 to 1 of rho cubed sine phi d rho d phi. And so rho is going to become rho to the 4th over 4 when we take an antiderivative, and we're just going to plug in 1. So that's just going to give us a factor of 1/4, which comes out here to give us a factor of 1/2. So this is going to be pi times k all over 2. Okay, and then we're just integrating sine from 0 to pi over 4. Which, okay, so an antiderivative is going to be minus cosine. Let's just do some scratch over here. So we're just evaluating minus cosine of phi from 0 to pi over 4, which is minus root 2 over 2. And then that's going to be plus, well, just cosine of 0, which is 1. Okay, so it looks like this is just going to be 1 minus root 2 over 2. And so our final answer will be pi k over 2 times 1 minus root 2 over 2. Okay, so that is going to be the mass of this region here that we called R. All right, so here we want to find the centroid of this triangle. And so before we talk about the centroid, let's actually just draw this triangle. I don't know about you, but it's kind of a relief when you just have something in 2 dimensions. After having to think about in 3 dimensions, it's like, oh, this is just in 2 dimensions. Somehow it seems more doable to me. Or I can just kind of relax a little bit and just think about things that I'm a little bit more comfortable with. So the vertices are 0, 0, and then 1, 0, and then 2, 1, like that. Yeah, so here's our triangle. And we want to think about this as like, you know, kind of like a plate, triangular plate. And so what is the centroid? So recall the centroid is the center of mass, assuming that the density is uniform. So this is just like a piece of sheet metal that's uniform. It has constant density. And the centroid, we want to see the point. You know, it's going to be somewhere, maybe right there. And the cool thing is that is the point that if I place a pin at that point, the plate, triangular plate, will bounce at that point. And so the coordinates of the center of mass, or the centroid, as it's called when it's uniform, is x bar, y bar. And we know what x bar and y bar are. So x bar is the integral over the region, which the region is this triangle, of just the function x over a mass unit, and then mass element, and then divided by the mass. And then the same thing for y bar, except we put in y. Somehow we're just averaging where the x coordinate of where all the mass is and averaging the where the y coordinate of all the mass is. That's at least the way I think about it, and it helps to kind of remember the formula and think about what's going on. So notice that, you know, one thing we have to do is we have to figure out what is the mass of this triangle for, you know, whether or not I'm finding the x coordinate of the center of mass or the y coordinate of the center of mass or centroid. I need the mass. So let's just find the mass. So the mass is equal to, well, the volume, or sorry, the area times the density. And recall we use sigma for density per unit area. So it's just sigma times the volume. Okay, so I need the volume. Oh my goodness, not the volume, the area. So what is the area? Well, it's just the double integral over this region of an area element. And now where do my area elements go between? Well, if I fix, say, a y coordinate here, then x is going to go from here to here. All right, so for a fixed y between 0 and 1. Okay. Then x is going from, what is this line? This line has a slope 2y in the yx plane. So I'm going from, this is 2y, or just think this is y equals x over 2. I'm going up 1 over 2, so then x is 2y, so 2y, and then this is y plus 1. Well, it's really x, and then the y coordinate would be minus 1, but then we solve for x. It's going to be y plus 1, and this is dx dy. Okay, so this is 0 to 1 of, let's see, y plus 1 minus 2y, so that should just be 1 minus y. Okay, but this is just going to be 1 minus a half, so 1/2 is the mass of this triangular plate. Sorry, that's the area. The mass is then sigma over 2. So the mass per unit area divided by 2. All right. Which means when I find or when I go to find x bar, I need to divide by the mass, or in other words, I need to multiply by 2 over sigma. And then I can use my same bounds, so I'm still integrating just from 0 to 1, 2y to y plus 1. So I'm just looking at this upper integral here, but I'm putting in a weight of x. And then dx, dy. So in other words, this is 2 over sigma, integrate from 0 to 1. This is going to be x squared over 2, so I'll have 1/2, and then y plus 1 squared minus 2y squared dy. Okay, and then this 1/2 will cancel with that 2. Yeah, and I'm sorry, there's also a sigma here, right? So dm is dx dy times sigma. So the sigmas will actually cancel. So we'll do that on the next line. So we'll cancel the sigmas, which is what we expect to happen. But yeah, so I mean, just a reminder, so dm is dA, which is dx times dy times sigma. But then, I get a sigma from the mass and they cancel. Okay, so then also the 2's will cancel, and so I just have the integral from 0 to 1. This is going to be y squared plus 2y plus 1 minus 4y squared. So in other words, 2y plus 1 minus 3y squared. Okay, and this is going to give me 1 plus 1 minus 1, so I'm going to get 1. So the x-coordinate of the center of mass is 1. Okay, and then I'll just find the y-coordinate of the center of mass, which again, if we can expedite the process, notice that, okay, the dm here is really dA times sigma, but I'm going to be multiplying by 2 over sigma, so the sigmas are going to cancel. And so I'm just going to have 2 times the integral from 0 to 1, and then the integral from 2y to y plus 1, this time of y, dx dy. And again, the sigmas are canceled. And so I have 2 times the integral from 0 to 1. What do we get here? I just get y times y plus 1 minus 2y, which is just 1 minus y. Okay, so that's 2 times 0 to 1, y minus y squared. And then this is going to be 2, this is going to be 1/2 minus 1/3. In other words, it's 1 minus 2/3, or 1/3. So the y-coordinate of the center of mass is 1/3. And you can kind of see, it makes sense. So 1/3 is about here, and 1 is there. So there is the centroid, or center of mass, right there. All right, so we get to compute some moments of inertia. First of a solid uniform cylinder, radius r and mass m, and the next a solid uniform sphere, a radius r and mass m. And now actually we're going to do the cylinder first, because now we can do the sphere by itself, but we can actually use the result from the cylinder to make the computation for the sphere a little bit easier. So let's start with the cylinder. And again, I'm not going to try to draw in 3 dimensions. I'm going to draw a cross-section of the cylinder. So the cylinder, if this is the z-axis, and this is, say, the y-axis, well, the cylinder is basically just a rectangle that we rotate around the z-axis. around, with respect to theta. We rotate in the theta direction around the z-axis. Okay, so what I want to do is I want to take a mass element. So first of all, what are we doing to find the moment of inertia? Well, the moment of inertia, I just add up all of the elements of the moment of inertia. That's kind of a silly thing to say, over the cylinder. What am I really doing? I'm integrating the distance away from the axis of rotation, and so let me specify the axis of rotation should be here along the center. So we're turning this way. Axis of rotation. So r is the distance from the axis of rotation, and here I've kind of set it up so that it actually corresponds to the polar coordinate r. And then I integrate r squared over the mass elements that make up the cylinder. And so I want to isolate a mass element that's a constant distance away from the axis of rotation. So what I'm going to do is I'm going to take this little slice right here. And now when I say this little slice, I really mean the slice that is now rotated around 2 pi radians or 360 degrees. And that's going to sort of be a representative mass element for the entire cylinder. Or actually, maybe just to make it a little bit clearer, I'm just going to take a little mass element like this. I realize I was actually skipping a step by doing that. So let me not even skip a step, just to show you exactly what's going on. So I really am just taking a small little mass element, which, recall, is the density times the volume element that's making this up. And then I'm just going to add all these mass elements up, or in other words, because it's a uniform cylinder, I can just add up all the volume elements because the density will be constant, using cylindrical coordinates. So, what we can say is that this is minus h over 2 down here, and this is h over 2 up here, because the height is h, and then this right here is big R, the big radius of the cylinder. Okay, so let me set up the triple integral. So I'm taking, well, let's just write this one more time. So r squared times delta, and then over the volume elements dv. The delta I can factor out, and now I just want to express everything in terms of cylindrical coordinates. So we have delta that we factored out. Theta, not surprising, we're going from 0 to 2 pi. We're allowing the mass element to go all the way around the z-axis. And then where's r going between? Well, 0 and capital R. That's good. And then z is going from minus h over 2 to h over 2. Okay, and then what do we have? Well, we have r squared dz r dr d theta, or in other words, this is going to become r cubed. All right, so let's go ahead and compute this integral. So notice dz, I'm just going to evaluate z from h over 2 to minus h over 2. That's just going to give me h. So I'm just going to get a factor of h, so that's delta times h, and then 0 to 2 pi. Okay, good. And then I have 0 to r of r cubed dr d theta. And we can do this pretty quickly. So this is going to give me a capital R to the fourth over 4. So delta H R to the fourth over 4. And then I'm just integrating d theta from 0 to 2 pi, so that's just going to give me 2 pi. Or in other words, I have delta H R to the fourth pi divided by 2. Okay, so that's the answer, but I would like the answer to not depend on delta. And so actually I can express delta in terms of the mass, because I really want to express the moment of inertia involved with just the mass of the object, and maybe something about the dimensions. So notice that delta, well, recall that the mass is the density times the volume, which means that the density is just the mass divided by the volume of a cylinder. Well, what's the volume of a cylinder? It's pi r squared, capital R squared, h. So if I just plug in this for delta, notice what I get. The h cancels, 2 of the r's cancel, the pi cancels, and I actually just get 1/2 m r squared. So that is the moment of inertia of a solid, uniform cylinder of radius r and mass m. Okay, so let's compute the moment of inertia of a solid sphere. And this problem's a little bit more free-for-all. Maybe it's not for the faint of heart. I'm sure there's a way to sort of carefully connect it to everything I've been saying, but I think it kind of uses a trick. And it's one of those things that if you haven't done this before, it's really difficult to try to think of how to do it on your own. And as I sort of alluded to, we're actually going to use the result about the cylinder. So we know the moment of inertia of a cylinder. So what we are going to do is draw the cross-section of the sphere. Because of the symmetry about the z-axis, we really can just focus in on a cross-section. Okay, so here's the sphere. So when I draw this circle, I really mean sphere. And the axis of rotation will still take to be the positive z-axis. If I label this z and y, it doesn't really matter. That'll be z and y. And notice, this is actually really cool, I think anyway. Notice that, say right here, I can cut up the sphere into a bunch of cylinders that are spinning about the axis of rotation. Okay, so yeah, I mean that's really the trick here. Okay, and now what do we need to kind of observe? The radius. Okay, so the radius here is r. I know the big radius of the sphere is capital R. And of course, this dimension here is z. And so I sort of get like a nice right triangle thing going on there. Okay, so you kind of see that right triangle. So I have the z going up to the disk, and then I have the radius of the disk, and then sort of the big radius of the sphere going out that way. Okay, well that's just, maybe to help you visualize what I'm about to do. But what I'm going to do is I'm going to say the moment of inertia of the sphere is, well, I'm just going to integrate over the sphere a bunch of things which I'm calling di. And what I'm going to call di is actually going to be the moment of inertia of this disk that has mass dm. So this dm the moment of inertia corresponding to this dm, I'm going to say di is, well, it is a cylinder. So the moment of inertia of this mass element is 1/2 r squared dm. So in other words, what I'm really doing is adding up over the sphere 1/2 r squared dm. Okay, so what is dm? Let's just keep going. Well, dm is, okay, so it's a disk. The height of the disk, notice, is dz. Okay, so that's, just a little change in z there. That's giving me, the differential element. And then it has radius r, so it's pi r squared dz, I believe. Pi r squared dz. Okay, so, I mean, this is why I say it's a little bit complicated if you haven't done something like this before, because, well, let me just fill all this in. So it's 1/2 integrate over the sphere. This is going to be, well, I also have a pi, right? Pi. Oh, and I'm forgetting one thing. Also have to multiply by the density. So I also have the density as a constant. So this is dV right here. To get the mass element, I got to multiply by the density. And then what do I have? I basically have r to the 4th dz. Well, this is a problem, right? Because my integrand is a function of r, and I'm integrating with respect to z. So what do I do? Well, now you see why I drew this triangle. So this triangle is giving me a relationship basically between r and z. So I know that r squared is r squared minus c squared by the Pythagorean theorem. And so r to the 4th is just going to be this quantity to the 2nd. So the integral I'm trying to evaluate is pi delta over 2, and then integrate. Okay, now I can actually put in my z limits. So z is going from, this is minus r up to r, minus r to r of r squared minus z squared all squared dz. All right, fun stuff. All right, so what are we going to do? What are we going to do? Okay, well, here's what I'm going to do. I'm going to expand this so I can actually integrate it. So I have pi delta over 2, integrate from minus r to r. This is r to the 4th minus 2 r squared z squared plus z to the 4th dz, okay, which, okay, minus, well, let's go ahead and take an antiderivative. So here we have, I'm going to try to skip a couple steps. I don't like doing this, but it's going to help. So here we're just going to pick up a z, and I'm going to evaluate from r to minus r. So that's going to give me 2r. So I'm going to have 2r to the 5th. And here I'm going to get a z cubed over 3. And then I'm going to, same sort of thing, evaluate from r to minus r. So that's going to give me a factor of 2. So I should have something like 4/3 r to the 5th. And then here, this is going to be z to the 5th over 5 from r to minus r. So again, I'm going to get a 2. So I should have 2/5 r to the 5th, not 4, 5. Okay, So I believe, you can fill in the details if you need to, but I believe that is correct. Yes, looking good. Okay, so what is this crazy constant here? Let's see, pi delta. Well, I can definitely cancel a 2, and I can factor out an r to the 5th. So I have 1 minus 2/3 plus 1/5. Okay, seems like I need to get a common denominator, so that would be 15. So I'm going to do some scratch word up here. So I have 15 over 15 minus 10 over 15 plus 3 over 15. So it looks like we have pi delta r to the 5th times 8 over 15. Yes, I believe that is correct. Good, so I didn't make a mistake. But now we just want the answer in terms of r and m, because that's what we're given. We're given the radius of the sphere, and we know the mass of the sphere. So, well, this is not so hard. We're going to do the same thing we did for the cylinder. So the density of the sphere is the mass of the sphere divided by the volume. And the volume, we know from exercise 1, is this. And so if I plug in delta, well, pi's gone, 3 of the r's are gone, and we're basically just going to get m r squared times 8 over 15 divided by 4/3. Well, that all in all is 2/5 m r squared. And so the last part of the problem said, which is going to roll down a hill faster? And of course, I'm assuming they're starting from rest. The sphere or the cylinder. So the cylinder had a moment of inertia 1/2 mr squared, which is larger than the moment of inertia of the sphere, which is 2/5 mr squared. 2/5 is smaller than 1/2. And so the sphere has a smaller moment of inertia because more of the mass is closer to the center of mass. And because of that property, having more of the mass being closer to the center of mass, meaning the moment of inertia is smaller, the sphere is going to rotate quicker, with the same amount of torque applied. And so the sphere, you will expect to roll down the hill faster than the cylinder.